Okay, diving straight back in. Let's spend a little time talking about chemistry. We have 8 weeks in the course, so 8 weeks of lectures and labs, and then the exam in the ninth week. That's 4 to 11 is 8 if you go inclusive, and then week 12 is the exam. So there are 4 topics, 4 fields in the science syllabus: chemistry, physics, biology, earth and space science. So what we're going to do, because we have 8 weeks and 4 topics, is spend about 2 weeks on each. So this one, I've called it Chemistry 1, and we're going to talk about some of the chemistry concepts this week, and then we'll talk about the rest of them next week. Now, what I haven't done is said, okay, Chemistry 1, we will do Year 7 and Year 8. Chemistry 2, we will do Year 9 and Year 10. Because the syllabus is a spiral. And so quite often you'll come back, you'll do a topic in Year 7 and then hit it again in Year 9 and then hit it again in Year 11 to deepen the understanding. So if I'd done Year 7 and 8 and then 9 and 10, I would have repeated myself and missed stuff because of the way that the thing spirals up. So rather than do that, I've divided up the concepts in a way that makes sense to me. Knowing my own understanding of the structure of the discipline. I understand chemistry, I have a sense of, and what I might do at some point, probably next week, is get you to draw a mind map of chemistry. How do the concepts relate to each other? So atoms, molecules, atomic structure, how does that relate to the periodic table? How does that relate to bonding? How does that relate to structure, properties of materials, and so on? So using the structure of the discipline is really helpful in planning teaching, but also using the level of conceptual understanding of students. We have theories like Piaget that talk about how students go from more concrete, less abstract thinking. They can think in terms of real objects and concrete things, to being able to imagine things in their mind and work with those, to manipulate objects mentally in their imagination and work with them. So we move from more concrete to more abstract as students go through. So what I'm trying to say is there are multiple ways to organize the content. This is why it's good that the syllabus gives us that freedom, that it doesn't dictate you must teach it in this order, because there are a range of ways in which you might want to change it in order to make the content accessible for your particular class, your particular teaching style, the resources that you've got, the time that you've got, a whole variety of other criteria. I just noticed that I can do this magic trick as well. Pretty cool. This is the video studio that I'm having some fun in. All right, so I'm going to firstly just talk a little bit about what the chemistry topics are in the syllabus, and then we're going to spend a bit of time on some of them. Again, this would be much more interactive with many more diagrams and asking people to do act outs and a whole variety of things were we in a room together, as I hope we will be. So for Year 7, for chemical sciences, there's only one sentence topic. So there is more emphasis on some of the other sciences in Year 7 than there are on chemistry. So there's one. Mixtures, including solutions, contain a combination of pure substances that can be separated using a range of techniques. So it's about mixtures and it's about separation techniques. And we're going to do a lab, I'm pretty sure it's this week or possibly next week, on separation techniques, a range of techniques used to separate. Now, I've included the elaborations here, of which there are several, but they're in pretty tiny print, so I'll kind of read out some bits and pieces from it, but I won't include the elaborations on the rest of them, and it's up to you to go and look at what those elaborations are. So the first one is kind of cool though, because it's investigating separation techniques used by Aboriginal and Torres Strait Islander peoples, such as hand picking. So you've got a basket of seeds, there are some stones that have been collected among the seeds, so you can hand pick and select and pull things out. We use that also. I had a job, which was one of the worst jobs I've done, which is lentils used to come along a conveyor belt, and I would have to pick out the stones from among the lentils for an 8-hour shift. So you would pick, throw, pick, throw, pick, throw, pick, throw, pick, throw. It became automated, but also because the thing was consistently moving across in front of your eyes would accommodate to that and decide that that was stationary. So when the belt stopped, everything around you looked as though it was going the opposite way, because your eyes kind of had adjusted to this constant motion. So it was a very weird and somewhat head-spinny kind of job to do, and a very, 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 very boring one. Music in the earphones helped a bit. So hand picking is a separation technique. It's a way of separating out different kinds of things. Sieving, so smaller things from bigger things. We sieve flour to get rid of lumps or break up lumps. We use filtration of various kinds. So a sieve is a coarse filter, but you could use filter paper for a finer filter that gets smaller particles out, and so on. Winnowing, I don't know if you've seen winnowing. It's a very ancient technique. It was used in ancient Israel and so on. Winnowing is taking the grain that you've got, putting it in a basket, throwing it up in the air and catching it again. But the wind is blowing, and the wind blows all the chaff, all the light stuff away, and just leaves the grains behind. So it's a way of getting all of the chaff out and away from the grain. So winnowing, yandying, which is a new one on me. Yandying is an Aboriginal practice, and it's basically, you know how panning for gold. So you put all of the stones and the gravel and junk in the pan, and you use water and spin it, and you spin all the other gravel out. But the gold, because it's heavier, goes to the bottom, and you keep the gold. Yandying is basically that, but without water, because a lot of the time was spent away from the water. So it's basically dry panning. You spin a shallow thing, and the heavy stuff goes to the bottom and stays in, the light stuff falls out over the side. And so you can separate things that way. Filtering, we talked about already. Cold pressing, so cold pressed juice or those kind of things, is just squeezing out the juice by applying pressure, not by applying heat or any other treatments. Distilling, so Indigenous peoples use distilling to get clean water at various stages. We use distilling to create spirits to drink, among other things, but to create medicines and a whole variety of things as well. So boil a liquid, turn it into its gas phase, and then cool the gas back to a liquid, but you've left impurities behind. The stuff that's gone up as steam is more pure, and so the stuff that drips out the end is more pure. So particularly because alcohol has a boiling point of about 60 degrees and water has a boiling point of about 100 degrees. So if you have done your sour mash or your whatever method of fermentation to create your whiskey, then you distill off the alcohol, you get a much stronger, much more alcohol in the distillate. You've left a lot of the water behind because of the different boiling points, right? Recognizing the difference between pure substances and mixtures and identifying symbols of each, identifying solute and solvent, I said it the wrong way around, solvent and solute in solutions, identifying and using a range of physical separation techniques such as filtration, decantation. Decantation, you pour a liquid off the crap in the bottom. We sometimes do it with wine. If a wine has some lees or some yeast or stuff in the bottom, we pour the wine off and leave the stuff in the bottom. Some of the beers that leave yeast in the bottle, we do the same thing. Evaporation, which is kind of half of distillation but without the catching, if you want the thing that's at the bottom. So you can drive off the water and keep the salt, for example, if you're trying to get salt from salt water. Crystallization, similarly, you drive off the water and keep the crystals of whatever it is. Chromatography uses paper or a medium, something, and allows things to filter up through it. And some things move faster and farther than others. So you can separate out things using chromatography. Distillation, talked about already, and separation methods used at home. So how do you separate things? There's another one called, I'm just trying to think what it's called. Maybe I've talked about it later. It's like decantation, but if you have oil and water, you can have a separation funnel and just release of the two liquids that won't mix, you can separate out one from the other. You could probably decant as well. You could pour the oil off the vinegar in a salad dressing if you put too much in, for example. Separation methods used in the home. Okay, so this is all of that is just year 7 stuff. So you can see that even though there's the one sentence, this is the topic to be taught this year in chemistry for year 7, there's a lot underlying that. There's a lot of information to be had there. So this is the year 8 one. There are 3 properties of states of matter can be explained in terms of motion of particles, differences between elements and Elements, compounds, and mixtures are at particle level, and chemical change involves reactions. Substances reacting to form new substances. So that's year 8. Year 9, properties of the states of matter can be explained in terms of the motion and a range of particles. So you can see the particle model is coming up, and we're going to talk about that today. Reactions are coming up. We're going to talk about those next week. Differences between elements and compounds and mixtures can be described at the particle level. That seems awfully like year 8. I reckon I've made a mistake there. Apologies. I will get the year 9 ones and put them and fix this PowerPoint. Should have mentioned that all the PowerPoints for the course will be on the course website in a folder for each week. I try not to overly rely on PowerPoint, but it is probably a helpful thing for you to have to study for the exam and so on. So that's probably not year 9, it's probably year 8. And we'll have to talk about what year 9 has. And year 10, atomic structure and properties of elements are used to organize them in the periodic table. We'll talk about the periodic table of the elements next week. And different types of chemical reactions are used to produce a range of products and can occur at different rates. So we'll talk about reactions and rates of reaction next week as well. When you're thinking about chemistry or teaching a science in general, it can be really daunting to try and get all of that. So if you took all of those topics across the 4 years, or even just for 1 year, and all the elaborations and all the resources and everything that you know about it, and remembering the science as a human endeavor and the science inquiry skills stuff as well, seems big and daunting. What you want students to take away is not factoids. I really don't care if students memorize the first 20 elements of the periodic table. I did when I was a student, and it's come in handy every now and then. But, memorizing facts or factoids. I use the word factoids. A factoid is a fact shorn of all connection. It's a pub trivia answer. It's a fact that doesn't actually connect to much of anything. Learning factoids is the least interesting and useful thing we do in school. What we really want to learn is ways of understanding the world. You really want your perspective to be changed. You want your students to see the world in a new way because they understand the science. So big ideas of chemistry education are everything is made of chemicals. You'll see people say, oh no, don't get that orange juice, it's got chemicals in it. Which is quite an ignorant perspective. Everything is made of chemicals. We are chemical substances. We ourselves are made of chemical substances. We're mostly hydrogen, oxygen, nitrogen, carbon, but we have trace amounts of sodium and potassium and magnesium that are very crucial for our functioning. We have a large number of different elements in us. We're made out of chemicals, the air's made out of chemicals, the sun's made out of chemicals, the lectern's made out of chemicals, the video camera, everything that's a thing is a chemical substance. The doped silicon semiconductor on the memory stick that this video is recorded on is a chemical substance. Everything's made out of chemicals. So students need to understand that, partly because it makes it compelling for them. Because if chemicals are just strange colored liquids in strange chemical glassware over there that chemists deal with, how compelling is that for every student in your class? It might be compelling for the 1 or 2 nerds who are going to be chemists, and I'm one of those, so I can say it. But it's not really compelling for students in general. But if everything is made out of chemicals, if everything they want to deal with, so if the student who wants to be a tattoo artist understands that ink is made out of chemicals, if the student who wants to be a skateboarder understands that different wheel materials, plastics versus polyurethanes versus whatever they're using these days, my skateboarding knowledge is quite out of date, understands that the deck is made out of materials, that all of materials have particular uses and particular purposes and costs and benefits and a whole variety of things, then the students are going to understand that it's actually relevant to their own lives. So everything is made of chemicals, everything is made of particles. So the particle model is very powerful. It's one of the big ideas of all of science. So we explain things in physics and in biology and in earth and space science in terms of the particle model as well. So the notion that everything, including us, is made out of tiny particles is also a really powerful idea for explaining what happens and why it happens. So we'll talk about that a bit more in a moment. And the properties of materials at the macro level. The properties of the fact that I can push on my face and my finger won't poke through is explained by the fact that there are electrons in the tip of my finger and electrons in the side of my face that repel each other. And so I can't push through because there's a force, an electrostatic force between those tiny particles in those materials. So the behavior of materials, silicon slime, why an egg is soft and then you heat it and it goes hard. All of that is explained by what's going on at this molecular and atomic level. I was going to say microscopic level, but we can't see atoms and molecules with a microscope. It's a sub-microscopic level. So the molecular level is probably the best way to talk about it as a shorthand. But things that happen at that level explain our experiences, explain why things behave the way they do. So these are the big ideas. If the students go away with these ideas, as I say, it doesn't matter if they know that carbon is element number 6. It's handy to know, but it's not crucial. It's much more important that they understand that carbon is a material that can make 4 bonds and therefore can make chains and networks and therefore has these particular properties and therefore can make the diamond that's on the engagement ring as well as the graphite that's in the pencil. So do you know what I'm saying? That understanding what the particles are, what their properties are, and how they explain the properties of the materials, how the pencil and the diamond ring are the same thing, is powerful, engaging, interesting, worthwhile learning for students. So the particle model. We talk about the 3 states of matter, solid, liquid, and gas, but there are probably about 7 altogether. There is solid, liquid, and gas are the ones that we deal with in our lives because we live on a planet that's in the Goldilocks zone around the sun. The Goldilocks zone is the zone in which water can be liquid. So in other words, the zone where over much of the planet temperatures are between 0, where water freezes, and 100, where water boils. So we live in that. We live in an average of about 20 degrees C, roughly. So mostly we deal with those 3 states. We can make ice in the fridge, so we have the solid state of water. Obviously, we have the solid state of steel in our cars and motorbikes and buildings, etc. We have the solid state of a whole variety of things. We have the liquid state of water, the oceans, massive part of the whole world. The liquid state of mercury, which is a metal that's liquid at room temperature. The liquid state of gallium, which is a metal that's liquid at slightly above room temperature. So you can take a chunk of it and put it in your hand and it will melt. So we have the liquid state of a number of things, and then we have the gas state of the atmosphere, pardon me. Speaking of the gas state, I just burped, pardon me. We have the gas state of the atmosphere. We have the gas state of carbon dioxide in fizzy drinks, which make us burp. We have the gas state of natural gas or liquefied petroleum gas that we use to run vehicles or heat up the barbie or a whole variety of other things, and so on. Now, plasma, though, is a 4th state of matter, and it's the most common one in the universe by far. 99.9999% of the universe is in the plasma state because that's the state that stars are in. Plasma is at very high temperatures where the electrons dissociate from the atoms. So you've got basically free electrons and free atomic nuclei moving around. So that's a plasma state. We get it in things like plasma balls. If you've seen those balls where you get the little sort of lightning thing going on inside them and you can touch it and it will come to your finger and all that stuff. So we see plasma in that state. That plasma is created by having a very low pressure and having particular gases. So it doesn't require high pressure. But generally, plasmas are at high temperature. And the high temperature is on stars because stars are undergoing nuclear fusion and they're very hot. And because stars make up the great multitude of the mass of the universe, because most of it's empty space, but of where there is stuff, it's star stuff mostly. It's not planet stuff mostly. So plasma is the most common state in the universe by some distance. Bose-Einstein condensate, on the other hand, happens at very, very cold temperatures approaching absolute 0, minus 273.15 if you want to be super technical. Minus 273 degrees, the coldest temperature you can get to in this universe. You cannot get colder than absolute 0. A degree or so above absolute 0, you can get Bose-Einstein condensate, which is kind of the opposite of plasma. In plasma, everything's broken apart. In Bose-Einstein condensate, everything's come together. So the atoms and the molecules collapse in. There are a couple of others. There is the kind of matter that you get in a neutron star where everything is compressed by incredibly great gravity. So there's a number of other sort of more obscure. There are fermionic condensates as well, I believe. But in general, the states of matter we deal with are solid, liquid, and gas. And our students need to understand solid, liquid, and gas. It's probably handy for them to know about plasma as well. We explain these things in terms of particles. So in brief, in solids, the particles are close together. They're not moving much. They're not moving relative to each other. They're in some kind of lattice network often. They are vibrating in place because temperature is the vibration of particles, but they're not moving much relative past each other. That's what makes something solid. So it doesn't flow down and away. It stays in its shape. It keeps its own shape. In liquids, the particles are still close together. They're moving a bit more and they're moving past each other relative. So a liquid won't maintain its own shape, but it will take the shape of the container it's in. So if I take my coffee from my pot, which is about this round, and pour it into my mug, which is about this round, it will take the shape of the new container. The liquid will have a defined shape. It'll have a defined volume. It won't get bigger and smaller by much. But it'll take the shape of its container. That's because the particles are able to move past each other. In a gas, the particles are moving a lot. They're faster, they're colliding, they're far apart from each other, and so a gas will fill all of the available space. If there were a gas leak, let's say, I was going to go a bit more grosser and biological, but if there were a gas leak in this room, very quickly the entire room would fill with the gas. It would be mixing with the air in the room, but it would go to every corner of the room. It wouldn't be sitting in a pile like a solid. It wouldn't be sitting just at the bottom of the room, taking the shape of the bottom of the container like a liquid. It would be everywhere like a gas. And you see what I just did there. I explained the behavior of the macro, the solid, the liquid, the gas, by the molecular level. What are the particles doing? Are they sitting beside each other vibrating in a solid? Are they moving past each other close in liquid? Or are they bouncing off each other wildly like in a gas? Right? So we explain things using this particle model. When we add energy to a system, in whatever form, it ends up as heat energy. It degenerates and gets to heat energy, and heat energy is that vibration. So if I've got my solid and I start heating it, the particles will move more than they were. And that means the thing will get hotter. So if I've got, say, a lump of iron, and I start heating it, I'm heating it with a blowtorch or an electric arc or whatever I'm using to heat it. Initially, the particles are vibrating a small bit. Incidentally, absolute zero is the point at which the particles stop vibrating entirely. That's the explanation of what absolute zero actually is the point at which there is no further vibration. And since vibration is temperature, you can't get any colder than that because you can't get less vibratey than no vibration. So you've got zero vibration at absolute zero. You can't get even less vibration than no vibration. Does that make sense? That's kind of a little bit of a noodle twister, but hopefully helpful. I'm heating my lump of iron. The particles are moving more, so it's getting hotter. At some point, it gets to the melting point of iron, which I believe is about 800 degrees C. And at that point, there's enough energy that they can't just vibrate in place. They start moving past each other. My solid iron has become liquid iron. Right? You see that in iron mills, the big vats of kind of reddish, yellowish liquid iron. So I can pour it into molds, I can do things with it. I can do cast iron from my liquid iron. If I were to keep heating it, and I can't remember the boiling point of iron from memory, 3,600 degrees, it's quite high. I could have gaseous iron. I could have iron vapor. My particles would be moving around wildly. It would be extremely hot. It would be very nasty stuff to come in contact with. And I don't think I could do much with it, but I would have the gaseous state of iron. And this is true for pretty much everything. There are a few substances. Iodine, for example, goes straight from solid to gas. It sublimates. It doesn't go through a liquid phase at normal pressures. There are a few things like that. But in general, most materials go solid, liquid, gas, or else they burn. So some plastics, for example, you can't melt. but they'll burn before they'll actually melt. So different materials have different properties. They're explained by what's going on at that stage. And it takes a lot of energy to change state from solid to liquid to gas. And that means you get a lot of energy back when you change state back. So if you have gaseous water, for example, so that's steam. If you have the kettle boiling and you have the invisible bit, the bit just at the spout of the kettle where you can't see anything before the cloudy bit starts, right? Does that make sense? Because the cloudy bit is not real steam, it's water droplets. It's already recondensed into droplets. But real steam is gas state. So the gaseous state of water is colorless, invisible. So that the only bit that's actual steam, we call it all steam, but the only bit that's actual steam is that little tiny bit where you can't see anything. If you put your finger in there, you'll burn yourself very rapidly because the water that's coming out in gaseous state will change back to liquid state. And in doing so, it will give off a huge amount of energy into your finger and do nasty damage to it. So changes of state involve a lot of energy. And we'll talk maybe a little bit more about energy when we talk about rates of reaction next week. But hopefully what I'm trying to do is give you a sense of the power of this particle model. So it explains pressure, the relationship of pressure and volume and temperature. So if I have a balloon and it goes up high in the atmosphere where there's less pressure, it will grow because there's less pressure keeping the gas in. If I place it in a very cold place, it will shrink because the temperature causes the gas molecules to get closer together. I've mentioned the ideal gas model on the slide. I don't want to get into it in a huge amount of detail, but I've been assuming that the particles' only interaction is colliding. But there are other interactions if they're attracted to each other. So if they have, this one's positively charged, this one's negatively charged, they might be attracted. Or they're both negatively charged, they might be repelled, and so on. So there are ways in which they interact that aren't just collisions. But that's probably beyond, that's probably year 11 and 12 level. We probably won't get into that at this stage. Okay, and last piece, this you will hopefully be all very comfortable with. The idea that atoms have protons and neutrons in their nuclei and electrons orbiting those. If I were in a classroom, I'd be drawing a diagram right now. But the concept hopefully is not hugely complicated, that the protons, which have a positive charge, are in the nucleus. The neutrons, which have a neutral charge, a zero electric charge, are in the nucleus. The electrons, which have a negative charge, are orbiting around them. So we can charge objects. So if I have a balloon and rub it on what hair I've got, or someone with much more resplendent hair, or a woolen jumper or something, I can charge it and it will stick to the wall or stick to another balloon because I've separated out some of the charge. I've taken some of the negative away from some of the positive and given them charges. We'll talk about this more in physics, but charge explains why things chemically bond, why reactions occur, and we'll talk a bit more about this next week. Chemical elements have all atoms of the same structure. And again, we'll talk about this more when we talk about the periodic table. What an element is. A compound contains two or more elements combined. So an element is purely just one element. If I have a piece of gold, it's all gold. There's no other element involved. I have a sample of oxygen gas. It's all oxygen, there's nothing else, if it's a pure element. A compound has two things in it. So salt, sodium chloride, is a compound of the element sodium and the element chlorine to form a compound. Mixtures are different things combined, but not in ways that are chemically bonded to each other. They're just in the same place. So I could have a mixture of muesli and milk. There's no chemical bond there particularly. It's just in the same place. Or I could have a mixture, a muesli that has nuts and fruit and oats and whatever. That's a mixture. There's no chemical bond between those things that make it up, if that makes sense. We'll talk about some of this more as we go. Solute and solvent. The solute is the thing that's dissolved in a solution. So if I want to make a sugar solution, the solute will be sugar, the solvent will be water, the thing that dissolves things. Water is a very good solvent. It dissolves lots of things, not everything. If I wanted to make a solution of butter, water wouldn't work very well because the butter won't divide in it. And some things aren't soluble. So I can't really make a an iron solution by taking a bunch of iron ball bearings and dropping them in water. They won't dissolve. So some things are soluble, some things are not. Some things are soluble in some solvents and not in others. So if I wanted to make a solution of butter, I could dissolve it in cooking oil, canola or something, because those things are both what we call non-polar, and a rule of thumb is like dissolves like. So oily things will dissolve oily things generally, and watery things will dissolve watery things. That's a very rough rule of thumb, but it works surprisingly often. So if I wanted to dissolve oil, motor oil, I would do it in petrol. I wouldn't do it in water, for example, and so on. So that's all we mean by polar and non-polar. It's characteristics of the solute and the solvent that either are similar and allow them to dissolve each other, or are different and don't allow them to dissolve each other. We can go into a bit more detail if we need to, but hopefully that's helpful. Sorry, itchy nose. Okay, and briefly, I talked about those separation techniques, and I mentioned that I mentioned some other ones as well. Solvent extraction. If I could dissolve, let's see, we do it with iodine sometimes. It dissolves in water but not in oil. So if I've got oil that's contaminated with iodine, I can mix it with some water, shake the two together, and then they'll separate out because the oil floats on the water, but all the iodine's now in the water, and I can just run the water off and leave the oil behind. So I've used a solvent, a different solvent that works for that particular solute to extract something, to separate something. So there's a number of separation techniques, and as I say, we'll be spending some time on those in the lab. And next week, as I said, we'll get onto the periodic table, and we'll get onto reactions, rates of reaction, when reactions do and don't happen, and so on. Whew. All right, that's been a lot of videos. I reckon I probably have run close to the 2 hours between the three. I didn't really intend to, but hopefully, if I don't make it back from China, these will be helpful to you. If I do, then they'll be helpful to somebody, because I'll throw them up on YouTube, open. Anybody who wants them is welcome to find them. Thanks a lot. See ya. Have a great one. See you next week.